Welcome to Algebra 2, Semester 1, Unit 6, Section 5.7. Okay. We're at the top of page 1, 2, 3, 4, 5, 6, 7. This is the top of the 7th page of this packet. Basically, we're at the fundamental theorem of algebra. The theorem, just out of the book, here's how it states, then I'll explain what it means. If f of x is a polynomial of degree n, where n is greater than 0, then the equation f of x equals 0 has at least one solution in the set of complex numbers. Corollary, if f of x is a polynomial of degree n, where n is greater than 0, then the equation f of x equals 0 has exactly n solutions, provided that each solution repeated is counted at the number of times that it's repeated. Here's what that's saying. You know how to find the degree? If we have a third degree polynomial, then it will have 3 zeros, or 3 solutions. Okay? Now, I pointed this out the other day with quadratics in class, that there were 2 solutions, and that's why we were talking about that. So let's look at this one. Right away, we notice that this is a polynomial. The degree is 3. So we know that it's going to have 3 solutions. Okay? If we go ahead and we go to factor this, it's 4, so we could go 2 by 2. Let's try that. X cubed plus 5x squared, we could pull out a x squared. We have x plus 5 left. Move that over here, x plus 5. We can pull a plus 4 out. And we have x squared plus 4. And an x plus 5 equals 0. Now if we set each of those equal to 0, x plus 5 equals 0. Subtract 5 from each side, we get x equals negative 5. There's one of the 3 solutions. Now, we take x squared plus 4 equals 0. X squared equals negative 4. X equals, x equals plus or minus radical 4. So x, that should be a negative radical 4. So x equals, would bring that negative out as an I, plus or minus 2I. So we have 2 solutions there and 1 there. There's our 3 solutions. Okay. Next problem. This is 4 solutions because it's a 4th degree. Let's see if we can find those 4 solutions. We have x squared, x to the 4th. Now if we look here, 2 factors that multiply to be negative 36 and add to be 5, well, negative 36 and 1 would add to be 35, negative 18 and 2, negative 16, negative 12 and 3, how about negative 9 and 4? But if it was negative 9, that would be a negative 5. So we need to switch it to being positive 9x to the fourth, or x squared, minus 4x squared minus 36 equals 0. Now we factor out from the first two. X squared would have x squared plus 9 left. X squared plus 9 over here. That would be a minus 4. So we have x squared minus 4 times x squared plus 9 equals 0. This is a difference of two squares. So we have x minus 2 and x plus 2 and x squared plus 9. Now to look at our zeros, we set this equal to 0, we'll find x equals 2. We set this one to 0, x equals negative 2. And we set this one to 0, x squared plus 9 equals 0. Subtract 9 from each side. X squared equals negative 9. Square root each side. X equals plus or minus square root negative 9. We bring that negative out front. We have plus or minus an I from the negative, and the root of 9 is 3. So we have two roots there, another root there, and another root there. We have 4 roots because it was a fourth degree. And that's basically what the fundamental theorem of algebra says. So let's go on to finding some that are a little bit harder sometimes to find the roots to. You need to be able to factor all these or be able to find the roots. Sometimes it's going to rely on synthetic substitution to find those and the skills that you've already built. So on this one, we know that there will be 4 zeros. Now remember, graphically, those 4 zeros are where they're either crossing or touching, coming in tangent with the x-axis. Okay? So we say there's going to be 4 zeros. When we look at this, we could factor out an x cubed here, but it's going to leave x minus 8, and 8 won't go into 27, so that we know that we can't factor that way. So our next thing is to find our zeros. Again, we put the factors of the constant over the factors of the leading coefficient. Since the leading coefficient is 1, we can simply list the factors of the constant. So it would be plus or minus 1, plus or minus 3, plus or minus 9, plus or minus 27. So if we start with the first one, let's try taking 1 in here. Bring down our coefficients. We have a 1, a negative 8, a positive 18, and a negative 27. Now, one problem that you might have seen right there is going down in order. We have 4, 3, 2, but we don't have a 1. So we need to spread that negative 27 over and fill in for a 1 there. Remember, you have to have all the placeholders when you're doing synthetic division. So now we say 1 goes into 1, or not into 1, I'm sorry. We drop down the 1. Now we go 1 times 1 is 1. Negative 8 plus 1 is negative 7. 1 times negative 7 is negative 7. 18 minus 7 is 11. 11 times 1 is 11. 11 and 0 is 11. 1 times 11. And we see that we have a remainder. So this is not a factor. Positive 1 is not a factor. Does not mean that negative 1 would not be a factor. And since I'm just going through the list, I'm going to try the negative 1. So I have 1, negative 8, positive 18, 0, negative 27. Drop down the 1. 1 times negative 1 is negative 1. Negative 8 and negative 1 is negative 9. Negative 9 times negative 1 is positive 9. 18 plus 9 is 27. 27 times negative 1 is negative 27. Negative 27 and 0 is negative 27. Negative 1 times negative 27 is positive 27. That brings us 0. So now we know that negative 1 is one of the zeros. Okay, now I go into the next one. I'm going to take 3 right into these coefficients. That one's out since we have no remainder there. So we drop down 1. 1 times 3 is 3. 3 and negative 9 is negative 6. Negative 6 and positive 3 is negative 18. 27 and negative 18 is 9. 9 and 3 is positive 27. Ho-ho, we have another 0 right there. Okay, so at this point I'm down to 1x squared minus 6 plus 9, and that should be a minus 6x. So I can go ahead and factor. I've got these two zeros. I know that I have 2 more, and I can factor that with the shortcut x minus 3 times x minus 3. So I know that I have 2 more zeros at 3 and 3. So those are my 4 zeros. Okay. Next one, pause the video and try to do this one on your own. I'll set up your synthetic division for you real fast. Looking at our roots, we would have a plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, plus or minus 16. And let's just start with 1. Our coefficients would be 1. The next one would be 7. The next one would be 8. And next one is negative 16. We drop this down. 1 times 1 is 1. 7 plus 1 is 8. 8 times 1 is 8. 16 times 1 is 16. And we have a factor. So we know that 1 is a 0. X minus 1 would be the factor. Now we have x squared plus 8x plus 16. Well, this happens to be a perfect trinomial square, so it's x plus 4 times x plus 4. And then we bring down that x minus 1. And so we know that our zeros are at 1, negative 4, and negative 4. Now you might say, well, how can the graph be crossing at negative 4 twice? Here's what's happened. If you end up with an even number of zeros, that means that that graph is coming to negative 4 and just touching it, just going tangent. If it occurs just once, then it means that it actually crosses the x-axis. Okay? But when it happens twice, that tells us, or you don't even necessarily have to have it twice. If it's an even number of times, then it's tangent. If it's an odd number of times, then it crosses. Okay? Next page. Only 2 problems on this page. They get a little bit lengthy. we have a polynomial to the 5th degree. We have to look at all the possible zeros, so we take our constant over our leading coefficient. We would have possible zeros, plus or minus 1, plus or minus 2, plus or minus 7, plus or minus 14. See me if you're lost about how to get those. We have another video where we went over those. Okay, use synthetic division to find the actual zeros. So I always start with 1, and I bring down my coefficients. So I have, from this upper problem, I have 1 as my leading coefficient. My second coefficient is -4. Third is +4. Fourth is +10. Then -13. And then -14. I drop down the 1. 1 times 1 is 1. -4 and 1 is -3. -3 times 1 is -3. 4 minus 3 is 1. 1 times 1 is 1. 10 plus 1 is 11. 11 times 1 is 11. -13 plus +11 would be -2. -2 times 1 is -2. -2 and -14 is -16. Okay? Now, that means that that was not an even factor. It is not one of the zeros, so now we switch over to -1. -1 let me get all of these. +1, -4, +4. Again, these are your coefficients. +10, -13, -14. Okay, so we bring down the 1. 1 times -1 is -1. -1 and -4 is -5. -1 times -5 is +5. 4 plus 5 is 9. -1 times 9 is -9. -9 from 10 is 1. 1 times -1 is -1. -13 and -1 is -14. -1 times -14 is +14. That wipes out. So we know that that is a 0. -1 is a 0. Now we can take these new coefficients. Let's try our next factor, which would be 2. Drop down the 1. 1 times 2 is 2. 2 and -5 is -3. 2 and -3 is -6. 9 and -6 is 3. 2 times 3 is 6. 6 and 1 is 7. 7 times 2 is 14. We have another factor. Okay, now at that point, I would see this as, let's see, this would be that was x to the 5th, so this is x to the 4th, this is x to the 3rd. So I could go on. The one thing that's intriguing me is how this 1 and -1, the -1 worked and the 1 was not far off. I am thinking I want to try -1 again in case we have a tangent before I go into those larger numbers, because these all seem to be coming very close to it. I may even try the 2 again if necessary. I'd just like to get it into quadratic so that we can factor it real quickly. So let's try -1 one more time. Doesn't hurt to try 1 twice in case you've got 2 of it. So we drop down 1. And negative 1 times 1 is negative 1. Negative 1 and negative 3 is negative 4. Negative 4 and negative 1 is positive 4. That brings 7. It does work. Negative 1 times 7 is negative 7. So again, we have a factor of a negative 1. And that was somewhat of a guess. It was just that these were working so well, and the numbers seemed to be remaining pretty low, so I was taking a guess that this would be more adhering to a negative 1 than a 2, and much more so to 1 and 2 than to 7 and 14, just looking at the size of numbers that we were getting into. Now we have 1x squared minus 4x plus 7. Now, if we look at that, there are no factors that multiply to be positive 7 and add to be negative 4. So that brings me to using the quadratic formula. Remember, quadratic can be written in standard form, just as we did up above. And that this is A, this is B, this is C. Standard, like the standard alphabet. Now we have the quadratic formula, which says a negative boy couldn't decide whether or not to go to a radical party or B squared without 4 awesome chicks, because it all got over, whoops, shouldn't put it past the equal sign, at 2 a.m. Okay? A negative b would be negative negative 4, so that's positive 4, plus or minus b squared is 16. 4 times 1 times 7 is 28, all over 2. Now to simplify that, I'll write it in 2 separate fractions. So 4 over 2 is 2, plus or minus 16 minus 28 is at negative 12. Over 2. Well, negative 12 would break down to negative 1 times 2 times 2 times 3. The 2's can come out as a single 2. 3 will have to stay in. And this negative 1 should come out as an I. So back in our equation here, we have 2 plus or minus I over radical 3. And that's still over 2. Well, these two will cancel and reduce that. So we end up with our other 0 being, let's write it up here, 2 plus or minus I square root of 3. So those are 2 roots there. We have negative 1 as a root twice, and then we have 2 as a root. And it just occurs once. Okay? So, basically what that's saying, if you were to look at the graph, we know end behavior, because this is an odd polynomial, 5. That means that our end behavior is going to be going down this way, not this way. Just think your positive cube root. It's an odd degree, and it's a positive, so it's going to be going up and then down this way. So at negative 1, we can kind of picture this. It's going to be a tangent because we have 2 negative ones. It's going to do something like that. And we're just kind of guessing here. The positive 2 is another real root, and it occurs once. So the graph probably does something about like that. Again, it's just kind of an estimate of what it looks like. Okay, this not being a real root, this being a complex root. Okay, next one. Again, same kind of thing. I want to encourage you to do this one on your own. I'll get you started. Find all the possible rational zeros. You would take that 6 over 1, so it's basically 6, and find all of the factors. Turn off the video and do that. And there's the factors. Okay. Next, you would need to take each of these and do synthetic substitution or synthetic division. So go ahead and turn off the video and do that. And when you turn back on, I will have the zeros, but I want you to have them on scratch paper showing the work. If you have trouble getting those, please bring that scratch paper because we need to look at what you're doing. Okay, so we come up with actual zeros. We end up with 1, and then 1 again, and then a negative 2, and then we end up having to do the quadratic formula. So let me make sure that you plugged it in correct. It would be 2 plus or minus radical. I'm sorry, I didn't see that I was off the screen. 2 plus or minus radical 4 minus 12 all over 2. You should have ended up with your complex zeros as 1 plus or minus I radical 2. Okay? Here's your actual zeros, 1, 1, negative 2. Here's your complex zero, 1 plus or minus I radical 2. Okay? So see me if you're having trouble on that. I want you to go ahead and do the next one. Pause the video in between. Find all the possible rational zeros. It would be plus or minus 1, plus or minus 3, plus or minus 9. So as you plug those in, let's just go ahead and do one. We take the coefficients again, 1, 7, 15, and 9. And we just try out one of our zeros. So we have, let's try 1. Bring down 1. 1 times 1 is 1. 7 and 1 is 8. 8 and 1 is 8. 15 and 8 is 23. 23 and 1 is 32. Okay, that did not prove to be a factor. Let's try negative 1. Negative 1, let's get these coefficients, 1, 7, 15, and 9. 1 drops down to 1. 1 times negative 1 is negative 1. 7 and negative 1 is 6. 6 and negative 1 multiplied is negative 6. That makes 9. 9 times negative 1 is negative 9. So bingo, we have that one. One of our zeros is negative 1. Now you could go ahead and factor 1x squared plus 6x plus 9. That is a perfect trinomial square, so we have x plus 3, and x plus 3. That means our two other factors would be -3 and -3. So the graph line will be tangent at -3 and it will cross at -1. Okay? Complex conjugates theorem. Basically, this just says that if you have, I'm running out of lead. If you have a plus bi as an imaginary zero, then you also have a minus bi. You can see this in the fact right up here when we solved this one, complex zero, that you always have a 1 plus or minus that term. Okay? Just a couple more problems. Write a polynomial function of least degree that has rational coefficients and a leading coefficient of 1. So basically, what you're doing here, I actually want to skip down and do this first sample. Basically what you're doing here is you're putting them back into their factors and multiplying them out to give the polynomial. So if I say I've got the zeros -1, 2, and 4, then I remember then that means I've got the factors x plus 1, x minus 2, and x minus 4. So all that it's asking me to do is to multiply those back together and give me the polynomial that I started with. We're going backwards from what we just did. So I would go ahead and I would multiply x times x is x squared, just FOIL it. Outside, x times -2 is -2x, plus the inside plus 1x would be a -x. -2 times 1 is -2. So that gets the first two there. Now we need to multiply it by x minus 4. So we have x cubed minus x squared minus 2x. On the next row, we have -4 times x squared is -4x squared. -4 times -x is positive 4x. -4 times -2 is positive 8. Okay. Add these together, x cubed minus 5x squared. 4x and -2x would be plus 2x plus 2. No, I'm sorry, that was an 8. Couldn't read my scribbled out writing there. Okay? So that's exactly how we get that. It gets a little bit more complicated when you're looking at a radical or a complex zero. So let me show you how that works. Just how we said that these have the 0 value and not the x value. So we have, first off, the theorem that we just went through that says that if we have the Conjugates theorem or the Irrational Theorem, it says that if we have an a plus radical b, then we also have an a minus radical b. So we need to realize that as we're looking at these. Okay, so if we have this, we also have, I've got to find a sharper pencil. This one will work. We also have 2 minus radical 5. So we have x minus a 2 radical -5. And we have an x plus we have an x minus 2 plus radical 5. Almost got myself confused there, but it's a plus radical b or a minus radical b, so it's 2 minus radical 5 or 2 plus radical 5 as your root. And then our other 0 was 3, so it's x minus 3. Okay? Now we need to multiply these back together, and I really find that we have to do just a little bit of work with these. First off, I bring this term in like this because truly the whole term is being subtracted from the x. So the first thing that I do on that is I distribute that negative throughout. So I have x minus 2 plus radical 5 and x minus 2 minus radical 5. Now, if we group them slightly different, move those parentheses, which it won't matter due to the associative property, we can move parentheses around, so we can have x minus 2 plus radical 5 and x minus 2 minus radical 5. And what's cool here is this is a sum difference multiplication pattern, so we know that we have x minus 2 squared and then we just have minus radical 25 because it's your first squared, your last squared, and then the middle number got wiped away. Okay, so that's what comes out of there. And now radical 25 is minus 5. X minus 2 squared, if you remember when we were doing binomial squares, that would be x squared minus 4x plus 4. We're still multiplying by our other root here, which is, or our other 0, x minus 3. Now let's go ahead and combine this negative 5 and positive 4, so we have x squared minus 4x minus 1. Now we're going to multiply by x minus 3. Comes back to just our basic math again. X times x squared is x cubed. X times negative 4x is negative 4x squared. X times negative x is negative x. Okay? Negative 3 times x squared is negative 3x squared. Negative 3 times negative 4x is positive 12x. Negative 3 times negative 1 is positive 3. We add these together and we get x cubed minus 7x squared plus 11x plus 3. And that's the polynomial that we started out with. Now to check this, I'll make sure and show you in class how you would check it, but you basically plug in your zeros, the 3 and the 2 plus radical 5, plug them in for the x values and solve it, and you will end up with it equaling 0. So for class, I want you to go ahead and try number 2 and number 3, and then make sure and get my help on those. If you don't get the correct answer would be, let me write it down at the very bottom of the page. Well, no, I'll write it up here so that you haven't matched up with it. X cubed minus 6x squared plus 4x plus 16. And the next one, x cubed minus 9x squared plus 28x minus 30. Okay? So I want you to try those. Come to class ready to work in small group with them, but I'd like you to get as far as you can before you start to get stumped so that you have questions to ask me on those. It's not too difficult. I think the hardest part is understanding this move right here, and I don't want to keep doing that until I can actually work through it. I've got some manipulatives that we can use if necessary to help you understand that. So go as far as you can and then come to class with it. Next page we have one last thing to go over, the Descartes rule. This is really cool. The number of positive real roots or zeros is the number of changes in sign of coefficients of f of x. And the number of negative roots or negative zeros is the number of changes in signs of coefficients of f of negative x. I'm sorry, I'm starting to lose my voice. That's one reason I'm trying to finish this tape quickly. So let's just look at a couple examples. Go ahead and fill this in. Number of changes of sign of coefficients in f of negative x, just like the one up above it. Okay, so if we look at this, x f of positive x, we end up with one sign change, a positive and a negative. So it has one positive real zero. So when we go to solve it, we know once we've found the one positive real zero that we're done on the positives. Now if we switch this to an f of negative x, that would be a negative x cubed plus 2 times negative x minus 11. Go ahead and work that out. A negative x cubed is negative x cubed. Negative x times 2 would be a negative 2x minus 11. Notice there's no sign changes throughout all of this, so there are 0 negative real zeros or roots. Well, now that might help you to understand, we know how many imaginary roots we'll have. How would we know that? Let me ask you, how do you know how many total zeros you have? That 3 right there, remember, tells us the total zeros equals 3. So if the total zero equals 3 and we have 1 positive and 0 negative, that means we have 2 imaginary zeros. Okay? These are a little bit faster here, a little bit nice. So here we look at this, our leading coefficient, but our leading degree really is 4, so we know that we have 4 total zeros. Now we look at the number of sign changes. Here we have g of x. Let me just bring down the signs. We have a positive, a negative, a positive, a negative, and a positive. So we have 1, 2, 3, 4. So we have we have 4 positive real zeros. However, you could have less. If you look up here at the rule, it says, or less than this by an even number. So we could also have 2 or 0. Okay? So now we go to the g of negative x, and we work through that. Well, negative x to the 4th power That even root will wipe that out so that that's still a positive. A negative x cubed would be a negative x times negative 8 would be positive. Negative x squared will wipe itself out to being a positive. A negative x times a negative 3 would be a positive. And then we have positive 1. So we have 0 negative real roots. Or real zeros. So we also know that if we had 4 positive real roots, if we had 4 positive real roots, then we'd have 0 imaginary roots. If we had 2 positives, we'd have 2 imaginary. And if we had 0 positive, then we'd have 4 imaginary. So that at least gives us an idea when we go looking for the zeros or for the roots. Same thing, same word there. How many to be looking for in the different areas. Okay, that draws to a conclusion on that unit, or on that section 5.7. Thank you very much.